Hi everyone, so today's video is going to be on Argand diagrams, which includes modulus argument form and calculations building on Unit 1 knowledge of complex numbers, as well as loci and regions. In my opinion, this has potential to be a tricky topic, and I think it's probably one of the hardest Year 12 core topics, perhaps alongside vectors, simply because of the introduction to working in radians and with polar coordinates, the geometric approaches to problems, and simplifying hard problems down to circle geometry or linear graphs. With this in mind, I've noted some top tips for dealing with harder questions in this topic, although of course one of the best pieces of advice is to practice as much as possible. This is really one of those chapters where you should give the whole mixed exercise a good go and perhaps look for some extra exam questions too. So moving on to the top tips, the first and foremost important one is to always draw or sketch diagrams for these questions. This helps with the geometric approach, can help with visualizing, and often you can get marks for diagrams as well, and they ask you to draw them and shade regions and stuff as part of questions. Next we have always checking the required form. Is it Cartesian or modulus argument form? And remember that we want our cos theta plus I sine theta. So if you end up with a minus, it's worth changing it to a plus, because having a minus is not strictly modulus argument form. And also check if they need the principal argument, which means that we will have the argument in the range minus pi to pi, as opposed to 0 to 2 pi. And make sure your calculator is in radians mode, and get familiar with recognizing common angles and degrees and radians, and think geometrically. So for loci and regions, what coordinate geometry could you use in the problems? And the frequent ones which come up, we've got perpendicular bisectors, circles and triangles, and we'll see all of those in today's examples. And remember when to use dotted or solid lines for inequalities. So for our first question, we've been given two complex numbers and asked to express them in modulus argument form. So I will draw a diagram for this, but it doesn't look like I've left enough space, so I will probably end up having to rub something out, but let's just start by drawing the Argand diagram. So real axis and imaginary axis, 4 plus 2i is going to be somewhere here, and minus 3 plus I is going to be somewhere around here. So if we just draw in, this is going to be the argument of this one, and for this one, this angle here will be the argument that we're interested in. So for w equals 4 plus 2i, we start by finding the modulus of w, which is the square root of 4 squared plus 2 squared, which is root 20 or 2 root 5. And the argument of w is going to be inverse tan of 2 over 4. And remember to have your calculator in radians mode for this. So arctan of a half is 0.464 radians. And then for z is minus 3 plus I. So the modulus of z is square root of minus 3 squared plus 1 squared, which is root 10. And then argument of z is going to be inverse tan of, well, we want to find inverse tan of 1/3. So inverse tan of 1/3 is going to be 0.322 radians. But that's not the argument of z, because it's the angle measured anti-clockwise from the positive real axis. So it's this angle here, and therefore what we need to be doing is pi minus 0.322 radians. is going to give us the argument of z, which is pi minus, so we have 2.82 radians as our answer for z. So to then convert both of these into modulus argument form, we have w equals 2 root 5 cos 0.464 plus I sine 0.464. And then for the next one, we have z equals, modulus was root 10, so we have cos of 2.82 plus I sine 2.82. And if we needed to give our answers in the range of pi to minus pi, then we would subtract 2 pi radians from 2.82. So it doesn't tell us in this example that we need to give it in the principal argument, but if we did, that's what we would do. So these are our answers for w and z. So given these, the question then asks us to find the value of w over z, and to do that, we will remember our rule that when we're given complex numbers in modulus argument form, for w over z, we're going to divide the moduli to get the modulus of w over z, and we're going to subtract the arguments. So w over z is going to be whatever 2 root 5 over root 10 is, and we'll evaluate that in a second. And then we'll have 0.464 minus 2.82, which gives us minus 2.36 plus I sine minus 2.36. And if we put that into our calculator, we get the modulus as being root 2, and this will simplify to minus 1 minus I. If you evaluate the modulus argument version here, if you put that into your calculator, minus 1 minus I is what you get. Right, so for our next question, we've been told, given that the modulus of z minus 3 equals the modulus of z minus 6i, we need to sketch the locus of z and find the least possible value for the modulus of z. So first of all, what I'm going to quickly do is rewrite these. Oh, 1 second, Apple Pen switched off. As z minus 3 and z minus 6i, because that just highlights to us that when we draw our Argand diagram sketch, as we should, with our real and imaginary axes, then we are looking for where positive 3 and positive 6i, not the negatives, even though we have z minus 3. And we want to, we've been told that the modulus of each of these is the same, and therefore what we want to do, the geometry we'll be using, is finding the perpendicular bisector of these 2 points. So as in where we have this line, and we want to find the perpendicular bisector of it, although that's a pretty bad line. So somewhere along here is the line that we're interested in, because along that line is going to be equidistant from both of those points. So to do that, we know that we want the perpendicular bisector of 0, 3 and 6, 0. Oops, put those the wrong way around there. We want the perpendicular bisector of 3, 0 and 0, 6, which is, you can work out the average of those two values, but it should be quite clear that the midpoint is going to be 3 over 2, 3. And if we work out the gradient from 3, 0 to 0, 6 line segment, then it's going to be 6 minus 0 over 0 minus 3, which is minus 2. So the gradient for the perpendicular bisector is going to be 1/2. And we know the midpoint, so we know a point it passes through. And if we know the gradient and a point on a line, we can find the equation of the line. So 3 equals 1/2 3 over 2 plus c. So 3 equals 3/4 plus c. And c is 3 minus 3/4, which is going to be 9/4. So that tells us that what we want is line y equals 1/2 x plus 9 over 4. That's the perpendicular bisector. So that's the line that we need to sketch. And we've sketched it in red here, but all we need to do is label on the relevant points, which we've just said. So 3 over 2, 3 is there. And this is 0, 9 over 4 here. So that's the first part of the question. And now we need to find the least possible value of z. So I'm just going to erase some of the working where we worked out the equation of the line, because I didn't really leave enough room. Okay, so we need to find the least possible value for the modulus of z, and we know that it lies somewhere along that red line. Z lies somewhere along that red line, and we want to find the point on that line which is closest to 0, 0, because that's where the modulus of z will be the smallest. And again, some coordinate geometry intuition will tell us that the point on the perpendicular bisector closest to 0, 0, if you draw a line from 0, 0 to that point, it should be perpendicular to the perpendicular bisector. So what I mean by that is, if I just do a bit more of a close-up of the relevant part of the Argand diagram, then we have our line coming across here like this. Wait, let me draw a bit bigger. Like this. And let's say it's here is the closest point. Then this line here, that is a right angle. That is what we can ascertain about that. And we want to find the least possible value of modulus of z. So we know that this line here, this line is going to be perpendicular to perpendicular bisector. And so the gradient is going to be -2, because that's what we worked out earlier when we were doing our original line. And obviously it passes through the origin, so the equation of that line is therefore going to simply be y equals -2x. And we already know the equation of the perpendicular bisector, so all we now need to do is solve simultaneously to find z. And then finding the modulus of z from there should be pretty straightforward. So we have y equals -2x, and y equals, what was it, 1/2 x plus 9 over 4. So solving those two simultaneously, we have -2x equals 1/2 x plus 9 over 4, minus 5 over 2x equals 9 over 4. So x is going to be, and I'll just put this in my calculator so I don't make any silly mistakes. X is going to be minus 9 over 10. And therefore y is going to be 9 over 5. So that's the point we're interested in, and since we want the modulus of z, let me just quickly summarize. So z is minus 9 over 10 plus 9 over 5i. The modulus of z is therefore going to be the square root of minus 9 over 10 squared plus 9 over 5 squared. Which, again, putting that into my calculator, we have 9 squared plus 9 over 5 squared, which gives us a value for the modulus of z as 9 root 5 over 10, which is our final answer for the modulus of z. Moving on to the next question. Given that z plus 6i equals 4, find the maximum and minimum values for the modulus of z. Hence, find the range of values of theta for which the above condition and the argument of z minus 4 plus 2i equals theta have no common solutions. So to save a little bit of time here, I've just drawn the diagram in for you, but it's relatively straightforward. So we've been told the modulus of z plus 6i equals 4. So that is going to be geometrically a circle of radius 4 and centre minus 6 minus 6. And to find the maximum and minimum values of the modulus of z, we can imagine drawing a straight line from the origin to the centre of the circle that also goes through the circle like this. And here, because the circle is the locus of points, this distance here is going to be the minimum value of argz. Oh, sorry, not including that bit, but this bit here is going to be the minimum value of argz. And then if we add on this bit, that will give us the maximum value of argz. The modulus of z. So to find the distance from 0, 0 to minus 6, minus 6, we can use Pythagoras. So we'll have the square root of minus 6 squared plus minus 6 squared, which would give us a square root of 72, or 6 root 2. And that is going to be the minimum. That's going to be the distance to the centre. And therefore, minimum value of the modulus of z is going to be that distance minus the radius, because that is the distance from here to here. So it's 6 root 2. The radius was 4, so it's 6 root 2 minus 4. And then for the maximum value of mod z is going to be 6 root 2 plus 4. So those are our answers to the first part of the question. The next part of the question is slightly more complicated. It asks us to find the range of values of theta for which the above condition and arg of z minus 4 plus 2i equals theta have no common solutions. So the first thing I'm going to do is add to the diagram. And since we're not going to need this, I'll just make a bit more space by erasing it. And for the next part of the diagram, we will add on a point at, so for minus 4 plus 2i, we're interested in 4 minus 2, which is somewhere about there. 4 minus 2. And essentially, if we want to find the point of no common solutions, we can find the most extreme values of argz that will fit, and therefore if they're outside of that range, then there won't be any common solutions. So what I mean by that is we have this line here and this line just here. And the special thing about these lines is that they are tangential, or tangents to the circle, because if they're tangents to the circle, those will be the most they only pass through the circle at one point, and therefore anything outside of those won't intersect the circle at all, and there won't be any common solutions. So remember that for the argument of z, we're measuring from the positive real axis anti-clockwise. So as in this angle here, and then adding on this angle here. So it's quite easy to spot what the first boundary condition is. Because we know that the radius of the circle is 4, then this point here is going to be, and this is a right angle, by the way. And if I draw in this as well, remember, right angle between a tangent and its radius. So this is -6, -2. And since it's on the same horizontal level with 4 minus 2, this angle here, which I'll label θ1, is simply going to be 180 degrees. But since we should be working in radians, it's pi. Positive pi, because we're measuring anti-clockwise from the positive real axis. And for the other angle, we need to work out this angle here, which I'll label, I'm going to actually split this into 2 down here to make it easier to see what we're working with. So like that. And each of these angles is going to be alpha over 2. And we can use trigonometry to work out the values of alpha over 2 by using these right angle triangles that we've constructed. And then from there, all we need to do is use the information about that angle being pi, this angle here being pi, and we can then just add and subtract angles around a point to get the values that we're interested in. So to find alpha over 2, I'll just redraw that triangle a little bit easier for you to see what's happening. So we have this triangle here. We'll just label on the important values. This length here, that is the radius of the circle, which is 4. So that length is 4. This was obviously a right angle. And we want to find another length. So I think this length here is probably the next easiest one to find because it's horizontal. So we don't need to do any Pythagoras. We can say straight away, hopefully you can see why, that this length is 10. Because we're going from -6 to 4. And this is the angle that we're interested in. This is alpha over 2. And we can use inverse tan to find the value of that angle. So tan -1 of, this is the opposite and this is the adjacent. So 4 over 10 equals alpha over 2. So I'm not actually going to work out what that is yet because that's not our final answer, but alpha is going to be 2 lots of tan -1 of, well, that's 2/5, isn't it? And since the other angle which we're interested in, just going back to our original diagram over here, we want to find this angle here, which I'll label θ2. And so θ2 is going to be, if we measure it as a negative angle instead of a positive angle, then θ2 will be minus pi add alpha, because we're measuring clockwise. That's why I've started with minus pi, but then we've added on this bit again here. So theta 2 is minus pi plus alpha, and that's the other extreme value of theta in this case. So if we work out what those two are, we'll find that outside of that range, there are no common solutions. So just to compute this, inverse tan of 2/5 and multiply that by 2, we have minus pi add 0.76 radians. So that's minus 2.38 radians. Just three significant figures. So theta, if theta is less than pi, and where theta is less than minus 2.38, more than minus 2.38 radians. Wait, hang on a second. So theta over 2 is minus 2.38 radians. And if it's less than pi or more than minus 2.38, so yes, in this range, there are no common solutions. And that's the answer to that part of the question. So moving on to the next question, we've been asked to start by expressing the complex number 4 root 3 minus 4i in modulus argument form. And this bit here just means the principal argument. So we need it in the range, we need the argument to be in the range minus pi to pi. So w equals 4 root 3 minus 4i. So the modulus of w is going to be the square root of 4 root 3 squared plus minus 4 squared, which gives 8. And for the argument of w, we will do inverse tan of minus 4 over 4 root 3, which is obviously arctan of 1 over root 3. If we do that, we get minus pi over 6, which is in the correct range of minus pi to pi. So w is 8 cos minus pi over 6 plus I sine minus pi over 6. That is w in modulus argument form. For the next part, and I'll just erase this bit actually. For the next part, we go back to loci again. So show on a single Argand diagram the point representing w and the locus of points defined by arg of z plus 10i equals pi over 3. So, well, the first one's easy. W is 4 root 3 minus 4i. So, 4 root 3 is going to be around about 7, and minus 4i. So somewhere here. W can be somewhere here. And the locus of points defined by arg z plus 10i equals pi over 3. That is going to be a half line that we're interested in. So a half line to define argument of z. So what that is simply going to be is from 0 minus 10 is going to be a line which makes an angle to that horizontal of pi over 3, which is 60 degrees, if you're still getting comfortable with radians. So just to make it not pass through W, I'm going to exaggerate the angle slightly more. And this line here is the half line. And when you're drawing this, you must make sure that it does not go beyond here, because that would be incorrect, because then the argument would no longer be pi over 3. So you cannot do that bit there. It has to be just here. And this angle is pi over 3. That is the half line. And you can draw a small circle there to show that it doesn't include that point. And that is the locus of points. So then it says, hence determine the minimum distance of W from that locus. So again, as before, the minimum distance is going to be where this line here from the locus to W is perpendicular to the locus. That will be the minimum distance. So what we need to start by working out is a Cartesian equation of the locus. I think that's probably the best way to go, so that we're not working entirely geometrically. And this also leads on quite nicely to an explanation of part of Argand diagrams as well, to help you potentially understand it a little bit better. So in general, if we have a line here, and I'm just drawing a standard right angled triangle here, where theta is our argument, this is a right angle, and this length here would be the modulus. For a change in x of x, y is going to be x tan theta. So if we were expressing the gradient, the change in y over the change in x, that's going to be x tan theta, or delta x tan theta, over delta x, which is just tan theta. And this tells you that the gradient of a half line is always going to be tan theta in these cases. Although you do need to be careful if theta is obtuse, but it's always based on this idea of being around tan theta. So that's why that works. Based on that, we can express this half line in the form y equals x tan pi over 3 plus c. So tan of pi over 3 is root 3 because it's tan 60. So if we just rearrange that a little bit, we have root 3, 0 plus c. So c is going to be minus 10, which we know because it passes through the y-axis. So y equals x root 3 minus 10. That is the Cartesian equation of the half line. And to find the minimum distance of W from that locus, we want to find the perpendicular line to that locus which passes through W. So the gradient of that line is going to be minus 1 divided by root 3, so minus 1 over root 3. And we know that it passes through W, which we also know the value of. W is 4 root 3 minus 4i. So we have y equals, actually I'm just going to skip straight to finding c here, if that's all right. So we have minus 4 equals, then we have 4 root 3 times minus 1 over root 3 plus c. So c is minus 4 minus, and then the root 3 on the top and the root 3 on the bottom are going to cancel. So it's going to be minus 4. So c is therefore minus 8. Oh, sorry, no. It'll be minus 4. So c is 0. so C is 0. So that means that the equation of the other line is y equals minus 1 over root 3 x. And we need to find the point where the half line intersects with this equation here. And we can do that by solving them simultaneously. So we have y equals minus x over root 3, and we have y equals x root 3 minus 10. So you set them equal to each other. Minus x over root 3 equals x root 3 minus 10. So minus 1 over root, So subtracting x root 3 from both sides, we have x minus 1 over root 3 minus root 3 equals minus 10. So that will give x as being, so we have minus 1 over root 3 minus root 3, and it will be minus 10 divided by that value is 5 root 3 over 2. And based on that, y is going to be, well, it's minus x over root 3, so it's minus 5 over 2. So that's the point that we're interested in. We have 5 root 3 over 2 minus 5 over 2. And we want to find the perpendicular distance from that point to w, which we can finally go back to Pythagoras and work out the magnitude of that line fairly easily. So it's 5 root 3 over 2 minus 4 root 3 squared plus minus 5 over 2 minus 4 all squared. And if you calculate that, that should give you, so 5 root 3 over 2 minus 4 root 3 all squared plus minus 5 over 2, add 4 squared. Oh, that's a lovely number. It is just 3. So that is the answer to the question. What was it originally asking is to find the minimum distance of w from that locus. So the minimum distance is 3. So that's the minimum distance is 3 units. So I'm going to end this video here to avoid making it excessively long, but there will be a part 2 on Argand diagrams with just a few more questions, less than this video, to consolidate more. But I hope you found this video helpful. Thanks for watching, and I'll see you in the next one. Bye.